Anyway, so I'll give you this top 10 list, and if you look at the final review handout, it has a very comprehensive list of topics, but that list may be too long, so here's just 10 things, not in any particular order. These are not in order of importance. Okay, let's use the big board. All right, so here's my top 10 list. First is conditioning, right? Conditioning is the soul of statistics, so that did have to come first. And conditioning includes a lot of things, right? It includes conditional probability, it includes conditional expectation, it includes Bayes' rule, and even includes Markov chains in a certain sense because it was a certain conditional independence thing. Conditional independence versus independence. That's been, everywhere. Second, symmetry. Symmetry is powerful but dangerous, I like to say, because it's extremely powerful in a lot of problems where you'd have to do 100 pages of algebra if you don't see the symmetry, and 1 line if you see the symmetry. On the other hand, you don't want to start hallucinating symmetries that are not there, so you have to be careful. And third, random variables and their distributions, which is one possible 5-word title for the whole course. Fourth is stories. So we spend a lot of time on not only story proofs, but more importantly, the stories for each distribution, like the normal and gamma and Poisson and so on. They're extremely important because otherwise, right, there are infinitely many possible distributions we could have looked at. Why do we spend so much time on the Poissons and exponentials and stuff? It's because they had important stories. Otherwise, just write down anything that integrates to 1 and work with that. Why are some distributions more useful and important than others? It's because they have stories. Okay, fifth is linearity. Sixth is indicator random variables, which is one of my favorite tricks, as I think you know. It's extremely useful on interview problems and all kinds of stuff. Seventh is Lotus. Just an extremely useful tool for computing expectations. And eighth is law of large numbers. I just sort of had to put it there because and central limit theorem. These are the two most famous theorems in probability, possibly the two most important theorems in probability, but definitely the two most famous ones. And then 10th, Markov chains, which I spent the last few lectures on. Okay, so that's just a top 10 list, but it kind of partitions up kind of neatly that the first 4 all have to do with the big picture question of what is randomness, right? That's what, that's why probability is everywhere, is because randomness and uncertainty, and what is uncertainty, that's everywhere, right? How do we think about uncertainty? That's these 4. These 3 are all about computing expected values. Indicator random variables you can use for other purposes as well, but we were especially using it for computing expected values. And remember also that expected values doesn't just mean finding the average of the random variable, because if we want to find the standard deviation, then we need the variance, and to get the variance, we need to do expected values. So a lot of things more than just the average reduce back down to this. So computing averages. And then these last 3, I would describe these as talking about long-run behavior. That is, we have, by long run, I mean we have a lot of random variables. So here and here, we take the average of a large number of IID random variables and see what happens. How does it behave? And then for Markov chains, that's how they were originally designed. Markov's motivation was going 1 step beyond IID. You run this Markov chain just wandering around for a long time, right? It's not IID anymore generally, but it has this nice conditional structure that makes it very nice to work with. Okay, well anyway, that's a top 10 list. And let me know if any other questions come to mind in the meantime. But meanwhile, I'll draw a little picture. So we've been, doing Markov chains. So it's kind of natural to represent, our current state is stat 110, right? So this is the whole world of statistics at Harvard as a Markov chain, and we're here now, and it doesn't matter how you got here, right? All that matters is that you're here in stat 110. And then the question is saying, well, where are you going to be next semester or next year, things like that. What can you do from here? So I want to briefly mention, if you look at the prerequisites for stat courses above 110, most of them require 110, and there's reasons. There are very good reasons for that. And just give a few examples, both mentioning a little bit about the courses, just so that for some of you, it may be useful to know, but also just to show you a few examples. Okay, so where can you go from 110? Well, the most obvious follow-up is 111. 111 and 110, in a sense, should be a full-year course in probability and inference. It's going back to the very first day of class. I won't draw the diagram again, but on the very first day of class, I drew a picture about what's the difference between probability and statistical inference, and then they're kind of two sides of the same coin. In probability, we're saying, here's our model, and then we're saying, well, what's the probability that this will happen? What's the probability that will happen? On average, what's going to happen, right? Given that we're using this particular model, like with Poisson lambda or something, and assume lambda is known, or lambda has some distribution itself, but that distribution is known, and so on. Inference is about going the other way. Like you have data, and then you want to actually then say, estimate unknown parameters, right? Theta or lambda or whatever the parameter is unknown, okay? You want to estimate it, or you want to make predictions about future, like you have observations so far, but then in the future you're going to get more data, and you want to predict what that's going to look like. Okay, so those are questions of statistical inference. You can't do statistical inference unless you have probability, because it gives you both the language you need as well as a lot of the theorems. Universality of the uniform. I didn't introduce that to torture you or anything. I mean, it's a beautiful general result, but it's also very, very useful in statistical inference. So things like that. Okay, so that's 111. That's every spring. But just from 110 and 111 alone, they're both more on the mathematical side rather than like a course where you're actually learning how do you work with data. So another course I would especially recommend is 139, which is linear models, which has some overlap with econometrics, EC 1123, and in fact, we in STAT have been having discussions with the EC department for years about the issue of 139 versus 1123 because the EC department's policy is that you can't take both for credit, and the STAT department's policy is that you can take both for credit. So because the STAT perspective on this is that the points of view are sufficiently different that you should be able to do both, but that's a difference in point of view about the points of view. So anyway, I mean, you could include, 1123, 1126 here. I'm not going to list all the course numbers. You should have some course in regression and linear models is useful for all kinds of things. And 139 does not require 110, but if you've had 110, it gives you a much better understanding of what's going on. And similarly, if you look at like 1126, take a look at the course notes for that sometime. Everything is conditional expectation, right? So if you understand conditional expectation, then that's going to be extremely advantageous. 139, you're going to understand what's going on much better than other people in class who haven't had 110, although it's not required. So I mean, 139 is just a great course in actually just, ways to work with data, that you're actually using data on the computer. And one piece of advice, if you want any, in addition to everything else I'm saying, is to learn R. That's one of the best six-letter pieces of advice I can think of. So R is a statistical. I also recommend learning C, and so I recommend CS50 or learn C somewhere else as well. but we're talking about statistics right now, learn R. R is very, very different from C. R was designed by statisticians for statistical purposes in mind, completely different from C in flavor. It's easier in some ways, but sometimes that's a misconception, that sometimes people who have been doing C for years think they could just learn R in like a couple hours and be an R expert, and they approach it all wrong, because it's just a completely different mindset. Very, very different language. It's extremely powerful. Actually, I just saw a really interesting article yesterday that was arguing that learning R, it's not only incredibly useful, that it actually helps you become a better statistical thinker just by studying this language. I hadn't thought about it that way before, but actually that article convinced me that was true. So it's incredibly useful. Okay, a lot of the stat courses above one, a lot of the stat courses in general actually use R, and it's whether you do more stat or not, it's just an incredibly useful skill, getting more useful all the time. And R is free. You can find all kinds of very, very well-written tutorials and stuff like that for free. You can download it for free. And because it has this kind of free software culture, a lot of people are writing R packages and put them online for free, and so it keeps growing like that because it has this open source culture to it. Okay, that's 111, 139. These are in no particular order. 123, finance. If you have any interest in not offered this spring, but it will be offered next spring. Any interest at all in finance, you should definitely take 123. I don't need to talk more about it now because Stephen Blythe already gave the 123 preview. Although I would mention I really liked what he said at the end about, he said the two-dimensional lotus was the key to winning the Nobel Prize. So then I was happy I have lotus here. That includes the 2D one, right here. All-dimensional lotus is. Okay, that's the finance course. 115 is computational biology. It's a really nice, that's every spring. It's a really nice mixture of biology, computer science, and statistics. A lot of it, to understand what's going on there, a lot of it relies on Markov chains and Bayesian thinking, you know, the things we've been doing, like that email that I just sent. Markov chains are everywhere in biology these days. So if you're interested in biology and stat, that would be a good one. Well, what else do I want to mention? 171 is another natural follow-up. 171 is stochastic processes. So if you liked Markov chains, you know, but we only had 3 lectures on it, and 171, maybe they spend a month on Markov chains and then do a lot of other stochastic processes as well. So in a sense, that's you know, 111 is swapping to the other side of the coin, and 171 is continuing in kind of probability thinking, or you have random variables evolving over time, right? That's a stochastic process. Okay, so that's a really good stochastic process course. And any others I wanted to mention right now? I think that's good. And okay, so we have that little thing there. I want to do just a few quick examples of just kind of how probability shows up in some of these areas. Okay, so for example, let's take 139, and by 139 I mean 139, but I also mean more generally regression, which you could also see in econometrics or elsewhere. It's extremely widely used for analyzing data. And the first time I saw regression, I really hated it. I thought it was the ugliest thing ever, and I had no idea what was going on. To start with a really simple, relatively simple, like linear regression model, just for the simplest case, just to do an example, because it's not a regression course, we're looking at models like this: y equals beta 0 plus beta 1 x plus epsilon. There's be a linear beta 0 and beta 1 are constants, which are generally, we would think of those as unknown parameters, so, you know, trying to estimate. And, you know, the question is, you know, can you use x to predict y, right? So you have a pair x, y. Maybe you have 100 people in your study or something like that. Well, it doesn't have to be people, obviously, but you have 2 variables. You want to know how does x use x to predict y. That's a regression. And this would be a simple example of linear regression because this looks linear, right? And epsilon is because you're assuming that x is not going to perfectly tell you y, that there's some error term here, epsilon, where generally we would, in practice, people often assume that these epsilons are normal with mean 0, but you don't have to assume that necessarily. So sometimes normal might not be realistic. But let's assume a common assumption would be that at least they're centered at 0. So the expected value is 0. So on average, it's not going to be that the errors should be 0 on average is a natural and common assumption. But in particular, I want to assume that the expected value of epsilon given x is 0. So there's not certain values of x that are going to make the errors tend to be positive rather than negative, that kind of thing. So let's assume that. I mean, this would just be regression. Okay, and then I'm not going to do much with this, so I'm just going to show you very quickly how to just get some simple facts about this. So one thing we could do when we see this equation is to take the covariance of both sides with x. So I'm saying that these are the same random variable, okay? So I can do whatever I want to both sides. So if I take the covariance of both sides with x, well, covariance of a constant with anything is 0, so that part goes away. So we have the covariance of beta 1x with x plus the covariance of epsilon with x. This is just a quick review of properties of covariance. Beta 1 comes out. Covariance of x with itself is the variance. So that's beta 1 times the variance of x. And then let's think about the covariance of epsilon and x. I'll just do that over here, figure out what this is. Well, but I'm assuming that the conditional expectation is 0. By Adam's law, the unconditional expectation is also 0, right? Because it's E of epsilon is E of epsilon given x. That's just Adam's law equals 0. And so the covariance of epsilon and x is just the expected value of epsilon x, because the other term is 0, because epsilon has mean 0. And let's just quickly compute this expectation. Well, the strategy, again, should be condition on x, right? Adam's law. So we're just going to go E of epsilon x given x. Just a quick review of Adam's law. Take out what's known. Once we condition on x, the next is known. So this x pops out right there. But what's left is E of epsilon given x, which we assumed is 0. So now it's x times 0. X times 0 is 0, so this is just 0. So actually, it's plus 0 here. So that tells us that beta 1 equals the covariance. By symmetry, that's the covariance of xy divided by the variance of x. Okay? So that's a very quick derivation of this fact. And if you look in a lot of books that do regression, you're going to have a very ugly looking formula with summation signs. This is the population version rather than the sample version. Okay? And a lot of books, if they don't want to assume 110, then they're going to give the sample version of just here's the formula. It's the summation of some, xi minus something, yi minus, that kind of thing. And they'll either prove that thing in some long, tedious algebraic way, or they'll just say, we don't want to prove this. Here's the formula for you. And it just looks really ugly, right? It's hard to memorize it, and it's hard to understand where it came from. But it's just that. So, understanding this, then you actually understand where the things come from. Similarly, a lot of these formulas that looked really ugly at first, once you really understand what they're doing, a lot of times it's just a conditional expectation. And in particular, a lot of times it's just a projection, right? We drew the geometric picture. What does this conditional expectation mean geometrically? It's a projection. Projections are nice, right? So just understanding these things, you actually can understand what's going on. In particular, a few of you actually asked me for book recommendations, and if any of you want more specific book recommendations for anything, I like recommending books. I'm just going to mention one right now. I love this book, Mostly Harmless Econometrics. Have any of you read this book? It's really cheap, too. It's like $18 on Amazon last time I checked. This book is beautifully written, and I can't say that that's true about many econometrics books. This one is just beautifully written, and if you flip through this book sometime, what you'll see is that conditional expectation and Adam's law and Eve's law are everywhere. So it's all building on things we did here, and if you hadn't had that background, it would be much harder to understand what's going on there. But with that, then it's just Adam's law, Eve's law. It should all come together. Okay, so I wanted to mention one other course here, which is more of an obscure one, but I think it's an important one. It's only offered every other year. That's Stat 160. Stat 160 is survey sampling. It's very relevant for any of you who are interested in government and policy and things that would involve survey data, political polls, or other types of surveys. Sampling, right? Just to give you a quick example of how you can use 110 ideas, and I think this is actually a good review example too. I'm going to do one. And you can imagine, by the way, that stuff like hypergeometrics would come up a lot there, because you have this population and you're drawing a sample, right? Usually you're trying to learn something that's of some policy interest, right? Usually you cannot ask every person in the population what their opinion is, so you get a sample and then you try to infer to the population what can you do, right? So if you sample without replacement, we know that hypergeometrics come up very, very, very naturally, right? So here's just a quick example. It's kind of a different mindset from other parts of statistics where we assume IID, because we're assuming that we're sampling from a finite population. That is, we have this is one approach to it. There are some kind of foundational controversies about how do you approach this problem. We have a finite population. Well, of course it's a finite population. It's always a finite population, right? But a lot of times that gets ignored. You have a finite population, let's say, of people, and suppose that there are true values of something that you're interested in, that any character, that is, for each person you have some variable. It could be their height, their income, their opinion on some question, whatever you're studying. Let's say that the true values are y1 through yn, where capital N is the size of the population. And let's assume that each person has an ID number, like a social security number, so there's some well-defined way to list them out. And these are treated as non-random, at least in the approach we're talking about now. These are treated as fixed. These are just constants. But they're initially, they're unknown constants, right? We just assume each person has some fixed opinion, but we don't know what those opinions are yet. So what do? We draw a sample, right? We get a sample, okay? And there's many, many different ways to do that sampling, which we discussed in Stat 160. You get this sample, and then you try to infer to the population, and in practice, it may be extremely difficult to get a simple random sample, that is, where all samples of a certain size are equally likely, and it's not always necessarily even desirable to have a simple random sample. But anyway, let's just assume we have some sampling scheme where we get a sample of size lowercase n, okay? And so suppose our goal is to estimate the average of these. Or equivalently, assuming we know n, capital N, then it's equivalent to just say, try to estimate the sum. That is, we only get to collect a sample, but we want to estimate the total or average value of the entire population. So we want to estimate the sum of all the yj's, j equals 1 to n. Okay, that's the goal. Now, we have a sample of size n, and let's assume that the probability that person j, we have some ordering ID number for each person. The probability that person j is in the sample is pj, which we assume right now is known. And then, of course, in practice, pj might not be known, and you might have to estimate pj, and then you can ask what happens then. How do you deal with the fact that you don't know the true pj? Okay, that's more complicated. But let's assume that the true pj are known. So the simple random sampling would be the case when all the pj's are equal. That is, everyone is equally likely to be collected into your sample. But that may not be true. Some people may be much easier to sample than others. Some may be just some obscure, hard to reach, don't answer the phone in some obscure part of the country or something like that. Other people are easier to actually collect into your sample. Okay, so PJs may not all be equal. Okay, now then the claim is that, so suppose that our data are, we get like x1, I'll just say like x1, z1 through xn, zn be the data that you collect from your sample, where x is the y value. I'm using a different letter, x rather than y, just to indicate the x's are random variables, the y's are fixed. The x's are random because this is the first person you collect into your survey, but that person was randomly chosen with some probabilities, so the value has become random because of the sampling. Okay? And z is just their ID number. So xj is the y value that you're interested in, and zj is their ID number of that person. That is, who did we actually get? That's the setup. Okay, so a question that is of tremendous interest is, how do we get an unbiased estimator for the total? And the standard method that's used, that's based on a very, very clever trick, is to divide by the probability. That is, you sum up all your observations, x equals 1 to j equals 1 to n of xj, but you divide by the probability of getting that person. So in other words, if the values you observed were like 5, 10, and 15, and those had probabilities A, B, C, what you would do is like 5 divided by A plus 10 divided by B plus 15 divided by C. So these are the probabilities, P, Z, J. That's unbiased. So this just says take each measurement and divide by the probability that you actually got that person in your survey. Then that's unbiased. Okay, so let's prove that that's unbiased. We'll take the expectation, but this looks ugly. Like this is kind of an interesting thing here, because this denominator seems kind of tricky, because this is P sub Zj, where Zj is the ID number of that person. It's a random ID number. So in the denominator here, we have a random probability. How do we deal with that? Well, a simple way around that is to rewrite this using indicator random variables. So let's just rewrite this as the sum, not just over these values that you actually had. Let's sum over the entire population, j equals 1 to n. And let's sum yj, which is just a constant, divided by pj times ij, where ij is the indicator of person j being included. So that's exactly the same thing. In the sample. That's the same thing, because anyone who's not included just gets zeroed out. And anyone who is included, that's 1, and then it's just the same thing here. But now we got rid of, now it's just pj in the denominator. Easy to deal with. Pzj, that's a random probability. Pj, very simple. Okay, so now the expected value I'll just take the expected value of this, linearity, right? So I'm just going to swap the e and the sum by linearity. The expected value of ij, by definition, and fundamental bridge is the probability that person j is included in the sample. By definition, that's pj. So this is just pj over pj yj, done. So that's a very, very simple trick. just divide by these probabilities. This is used all over the place now. Variations on this trick is a very important idea. Inverse probability, this is either called Horvitz-Thompson estimator. We just derived the Horvitz-Thompson estimator. It wasn't too difficult. Or it's called inverse probability weighting, and you'll find there's tons and tons of people using this. Inverse probability weighting. Okay, well, I mean, so you can do that. That's unbiased. Now we come to a deeper question. Is unbiased good? Well, I mean, I'd rather be unbiased than biased, but is that good in and of itself as a criterion? Is that good enough to tell us, you know, that this is actually a good estimator? That's a much harder question. And I'll tell you a quick story showing that this can be horribly, horribly bad. I'm not saying it's always bad either. It can be good, it can be bad. I'm saying this goes much deeper. This is one of my favorite examples. This is called Basu's elephant. And Basu was one of my favorite statisticians. So I'll tell you Basu's elephant story quickly, just as an indication that there's more, you know, there's a lot going on here. Statistics cannot be described as like, you know, you learn some formulas and you plug it in and whatever. You need to think really hard about, does it make sense? Is this useful? You can't just say, oh, it's unbiased, so we're happy. Okay, so the story is, there was a circus owner who had 50 elephants, and he wanted to know that the average weight of his elephants. Equivalently, he wanted to know the total weight of the 50 elephants. And I've never tried weighing an elephant, but apparently it's, you know, pretty hard to actually physically weigh the elephant. There's too much work to try to weigh the 50 elephants. So the circus owner said, okay, I'll just take one who looks average. Let's call that elephant Stampy. Take Stampy, weigh Stampy, multiply by 50. Sounds like a reasonable thing to do, right? But a statistician overhears that and gets very, very agitated and says, that would be biased, right? And so the circus owner says, okay, you're the statistical expert, what should you do? And the statistician, this is actually not a very good statistician, it's one who just kind of learned some formulas and says, well, you should use the Horvitz-Thompson, you know, we do this inverse probability weighting, well, you know, thing, otherwise you're gonna be biased, okay? And the circus owner says, well, I really want to weigh Stampy. He's right here, you know. The other elephants are off wandering somewhere else. I really like Stampy's, you know, not going to kick me and stuff. So anyway, then the statistician says, that's fine. In this Horvitz-Thompson, these probabilities, PJ, I should have written PJ greater than 0, because then we're not dividing by 0. But as long as PJ is greater than 0, this is perfectly fine. It's still unbiased. So they decide to give probability, they're only going to weigh one elephant. They decide to give probability 0.99 to Stampy, and then for the other 49 elephants, take the other 1% and divide that up equally to the other 49 elephants. Sure enough, 99% chance, they get to weigh Stampy. So they weigh Stampy, and everyone seems happy, until what the circus owner was proposing to do is take Stampy's weight, multiply by 50, right? Seems like a natural thing to do. The Horvitz-Thompson says, take Stampy's weight, divide by the probability, which was 99 over 100. So you just take Stampy and multiply by 100 over 99, which is just slightly greater than 1. Now that doesn't sound like a very good estimate for 50 elephants, just to take one of them and multiply by 100 over 99. And so the circus owner says, oh, there's something seems a little suspicious about, are you sure that that's good? And the statistician says, well, you know, if you'd gotten one of the other ones, well then you multiply by 4,900. So then, you know, it's unbiased. So, okay, so there are very, very, very tricky questions about, you know, what are kind of good criteria or natural criteria for when is an estimator good? What does that mean? That goes back into 111 a lot. 111 is going to be a lot about Bayesian versus frequentist. So we've been talking about some Bayesian stuff, right? Like we talked about conjugate priors and the beta binomial and things like that. They'll do a lot of conjugate priors, things like that. Unbiasedness is kind of inherently a frequentist concept, but there's other frequentist concepts as well. You can ask, you know, when when are these two methods or ideas? Well, first of all, you can discuss whether there even are well-defined methods, but when would they agree? When would they disagree? Things like that. There are very, very, very subtle questions that come up. Very, very surprising. There are a lot of paradoxes in like where you write down something that seems like a perfectly natural estimator, and then you can prove that actually you can always do better than that, and things like that. Okay. Well, so let's see. Any other courses to mention here? All right. So this is our little Markov chain for well, it's not really a question is whether it's irreducible, I guess. It's not irreducible right now. Now, of course, you could go from 111 to 139. You can go from 139 to 111. You can go all over the place. There are a couple more quick edges we should draw here. One is 110 goes to jobs. So if any of you get any good interview questions that relate to probability, please send them my way. I won't get into the whole vocational debate right now, which has been coming up more. And one more. The 110 is actually a recurrent state in this chain. And we have William is here, who took the class last year, so we have an example. Someone else just emailed me yesterday saying she took it last year and was like really wished more than anything she could just repeat the class over and over again. Now I'm hoping you're not going to repeat it over and over again in the sense that you actually have to literally retake the course, but in the sense of revisiting the material over and over again is a good thing. Okay, well, that's all. Thank you. It was all fun.